on this computer. All right, and now share screen so that it gets, no, screen one. There we go. Okay, so I don't do too much in the way of mathematics. I'm not a mathematics professor, but so problem 3. So I'm going to go over problem 3, and the same goes for problem 4. Okay, so problem 3 is actually a famous kind of it's a named, I should say, series for numbers. Plus n minus 1 n. Okay, it's a named series for numbers called the triangular number series. If you go to the Wikipedia page, you can find out all you need to know about it. But it is named thusly because of the arrangement of dots we can make. 1 plus 2 plus 3 plus 4 plus 5. So each additional number we add, 1, 2, 3, 4, 5, is arranged can be arranged like a triangle. This is why it's called the triangular number series. Now, this has a resultant formula. Okay, this has a formula, which is n times n plus 1 over 2. Now, we will see this formula kind of again and again in the algorithms we write. For instance, if I am writing, or we'll find something similar to it. For instance, if you wrote your unique function like this, where you check for I is equal to 0, I plus plus, right? This is your unique function. And then you had your secondary loop for j, and some people started with j is equal to 0 and they had another condition. But some people thought, wait a second. Okay, checking if a and b are equal is the same as checking if b and a are equal. So I don't have to recheck that, right? Yeah, so any j doesn't have to check anything behind it, is the point, right? If I'm starting at index 5, I don't have to check 5 against 0, 1, 2, 3, or 4 because I've already checked those, right? 0 has already checked with 5, so 5 does not need to check with 0. Okay, so I could start at j is equal to I plus 1, right? And the way this check works out is now that we've got, since we aren't ever going to check ourselves, the first item is going to check against n minus 1 other items. The second item, index 1, is going to check against all the other items, which is n minus 2 total items, dot, 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 until we get to the last couple of items where they're going to check against themselves. So it's this formula of just essentially minus 1 to everything in it, which is pretty close. We would just have to subtract. We're just literally subtracting 1 from every item in here. So we would just do minus 1 and minus 1 there, and it just kind of rewrites the formula. So it's very similar, where we have to compare everything to everything else. That's where we see this formula, and you can imagine how often that comes up. So, okay, now we see this a whole lot, but we have this formula, and we say that, hey, this number is this. So let's kind of just check that out. If we can check, we can test that for, let's test it for an easy number like 3, right? 1 plus 2 plus 3 is equal to 6, right? And so we can check it against this formula. 3 times 3 plus 1, which is of course 4, right, is equal to 12 over 2, right, which is also equal to 6. All I did was plug and chug with 3, right? I just simply plugged it into the equation. No, right? So we can see just with the trivial example that this works. Now, how do we derive? Honestly, I don't care how we derive it. What I want to show you is more how to prove these two things are. So first, I'm going to kind of show you the intuitive proof, which has to do with the triangular number series that we had, right? So so n times n plus 1, n plus 1 over 2, right? And now let me just draw that out, right? 1 plus 2. I'm just moving the dots a bit to make a bit of a different triangle. 3, 4, and now 5. And then repeat ad infinitum in this direction and this direction. At some point, though, we have n. We have a stopping point, n. We don't go to infinity. If we went to infinity, we'd get a different answer. Anyone know what that answer is? Yes.
Like in terms of,
yes,
like
where
if the problem was asking and it was an infinite series,
if this was an infinite series, where does it converge?
it doesn't converge.
It converges to -1 of 112. Yeah, I'll look it up. Seriously, go down a huge rabbit hole and get ready to read a bunch of think pieces about how it does not converge to that. But the answer is that it will converge under very specific circumstances to -112, which are useful in some. That answer is useless in most domains of mathematics and useful in some domains of mathematics. I used to understand why that was the case, but I no longer do. But Numberphile did a great video on that, and be prepared to read that a lot of people say that YouTube channel is wrong, but it is. But at the very least, you will learn something interesting about mathematics. But I need to prove it to you, of course, now, or at least show you that I am not being crazy. 1 plus 2 plus 3, ... -1 over 12. Let's see. To infinity. Yep, Ramajan summation will convert. It will triangular number. In particular, the methods of zeta function regularization and Ramajan summation assign the series a value of -1 over 12. So it is worth giving a it is worth taking a look at if mathematics is something you are into, and worth avoiding if you want to stay as far away from mathematics as possible. I should also mention, like, you don't need good math skills to be a programmer. Like, you don't need math to be a good programmer, or even a great programmer, but you need it if you want to be an amazing programmer or a wizard. Okay, so that's what it comes. You can be perfectly fine without having to deal with math, I'm saying. But if you want to deal with the heavy theoretical stuff, you need the math. And you can get great jobs as software engineers without having to worry about that math, is what I'm playing about. It all depends, but just really depends if you want to do the research or work in practical stuff. So anyway, let's go ahead and say this goes all the way to n, right? This would make kind of a square if I say that these series of dots comes out over here. And if I draw out this square, we'll see that this series of dots kind of occupies a bit more than a half of that square, right? That's kind of the visual proof of that before I got completely waylaid. But visual proofs aren't really proofs mathematically say. So what we're going to do is that we're going to prove by induction. Now, proof by induction is a two-step process for proving basically that two equations are equal to each other. There's two steps. First, and we have a base case. We have to prove for a base case that we have to prove that it works for a base case, which means that we have to have some starting point that it works at. Okay. Now, in recursion, we'll also be dealing with base cases. Like in recursion, things have to converge to base cases. Okay. So hence why they kind of go hand in hand. And the second is assume n, prove k plus 1. So assume that it's true for, sorry, not n. Assume it works for k, prove it's true for k plus 1. Okay. So this step, easy. This step, easy once you understand it. Okay. And it's okay if you don't understand it, because this is not my domain to make it you understand it. It is my domain to expose you to the idea. So let's choose base case. So what is the smallest number this would be true for? Well, we start at 1. So we're going to say, let's prove it for n is equal to 1, right? So 1 to n, which is 1, it's 1, right? This side of the equation, if I plug in 1, it's going to be 1. Okay. And then that's equal to n times n plus 1 over 2. Let's plug in 1 for each of these, 1 and 1. So that becomes 1 times, and we don't care because that's a constant factor, becomes 1 plus 1, which is 2, over 2, which becomes 1. Okay, so it holds for a base case, right? Again, math, I try not to deal with hard numbers, and so, you know, I just try. And just life hack for your exams, by the way, for your math exams. Professors don't like having to deal with difficult grading. So when in doubt, with a problem, and you're trying to solve for a specific number, the 5 choices that we'll often go for are 1, -1, half, -1/2, and 0. Those are because those are easy to grade. They're easy to recognize. You will find as you solve a number of equations on your exams correctly that those convert, that those crop up a lot because humans are lazy. Okay. All right, so now what we have to do is that we have to assume, now the second part, we assume it's true for k. In other words, we're going to replace our n's with k, and we're going to assume it's true for k. And we're going to say, okay, if it's true for k, we have to prove that this equation holds for k plus 1, which means we assume it's true for k. Now let me rewrite this and say we want to prove that if for k plus 1. So in other words, rewriting this equation plus k plus 1 minus 1, which of course just becomes k. So here I'm replacing the n's with k plus 1. Okay, got it? And plus k plus 1. So all I've done is replace all the k's, sorry, all the n's with k plus 1, which if I rewrite it, becomes much easier to read, k plus 1, right? And so now again, I need to replace in this equation all the n's with k plus 1. And I'm not going to break out this side of the equation. I'm not going to break this side of the equation yet, right? I'm not going to break those parentheses yet. So we've got, so notice all I've done is replace the n's with k plus 1, thus making it harder to read. Okay, that's all I've done. But I'm trying to say, hey, we assume it's true for k, so it must be true for k plus 1. So what does that give us? Well, it's that first part. Assume it's true for k. That is the trick. I assume it's true for k. This is part a subsequence over here. This is 1 plus 2 plus 3 ... k minus 1 plus k, right? That's what that is. And we assume that it's that our proposed state for this is true. Now, why does this matter? The whole assuming it's true for k, then it works for k plus 1. Well, if I can prove that if it's true for the preceding value, then it works for the secondary value. We proved that the base case works. So that means if we can prove this step, then that will prove that, then 1 will prove that it works for 2, and 2 will prove that it works for 3, and 3 will prove that it works for 4, and 4 will prove that it works for 5, and 5 will prove that it works for 6. Make sense? So kind of like it's a domino effect by saying that, hey, we've got a starting point, and then then if it's true for any starting point, then the next point works. Then it just kind of cascades and proves itself. So now we assume that it's true for k plus 1 so if we can assume that it works for k, that means I can rewrite this side of the equation from this infinite series. I can rewrite this as k times k plus 1 over 2. Makes sense? Because that is the infinite, this is the part we get to assume is true. We get this for free. And then this becomes plus k plus 1, right? That was the part that, and that is equal to k plus 1 over, times k plus 1 over 2. So which side shall we work on first, the left or the right? Doesn't really matter. Just tell me which one you'd want me to work on first. The right side? Cool. I'm going to FOIL this sucker. Okay. So, because I've got, so let's see, actually, I'm going to just distribute. Let's see, make it easy to, let's go ahead and break this apart, break those up. So let's see, I'm going to turn this into, instead of k plus 1 plus 1, I'm going to go ahead and turn it into k plus 2, that's right. And then I'm going to FOIL it so that it becomes easy for me to read, which is, actually, I'm not going to FOIL it. That'd be silly. I'm going to distribute instead. I'm going to, which is weird, but hold with me. And what do I mean by distribute it? So multiplying against the first value, I'm going to turn into k plus, so this was k plus 2. So I'm going to do k plus 1 times k plus k plus 1 times 2. Okay, so all I've done is taken that FOIL value and all I've taken this is just distributed across those two values. Okay, so I'm just avoiding like writing out k squared because that would be annoying. Okay, over here on this side, what am I going to do? I am going to go ahead and put this all over one denominator. To do so, in order to add them together, I have to make it a factor of 2, right? Which means multiplying this by 2. All I've done is multiply this. I've done an overcomplicated way of multiplying this by 1, right? So this becomes, so now I can rewrite this as k plus 1 over 2, which scratch that out, move it to the front. Hey, look at that. Scratch this out, move it to the front. It's the same thing. So I've got that my two sides equal, horribly drawn. This is why I type almost everything on the computer rather than writing it. But the point being is that the two sides are equal, which means it's true for k plus 1. So we've assumed it's true for k. So that means that since it works for 1, it works for 2, and if it works for 2, it works for 3. If it works for 3, it works for 4. If it works for 4, it works for 5. And so it works for any value of n. Now, going back to the important point for your question, right? So that convergent, this notation was kind of silly, right? We didn't, or sorry, not that. I to the n, I is equal to 1. That's what that was, right? This side doesn't really tell you much, which is what I wrote. But this side, for big O purposes, tells you everything you need to know, which is that is equal to n squared plus n over 2, which is, now if we distribute that, get rid of the smallest factor, sorry, get rid of all the smaller degrees, get rid of any constant factors, and put a big O over what remains, and that becomes big O of n squared. Similarly, for equation 4, we have a similar equation, which I'm trying to do this off the top of my head, so please correct me if I'm wrong. But if we look up 1 squared plus 2 squared plus 3 squared, it converges in much the same way. Typically, what happens is that that question 1 is done, that question 3 is done in your calculus class, and question 4 is given on the exam to prove via induction. Okay, that is given. So 1 squared plus 2 squared to n squared, right? That is given as, I believe, n times n plus, and again, correct me if I'm wrong, I'm going over from memory. N times n plus 1 times n plus 2 over 6. Now I'm sure about the 6 and about this. It's these two other factors that I forget. I forget what if it's plus 2 and plus 1 and plus 2, if it's minus 1 or something over there. So is that correct?
I think it's 2n plus 1 for the second.
2n plus 1.
For the second one. It's not plus 2, I think it's 2.
2n plus 1. Okay. Okay. I'll look it up. But the point being is that if we have three n's multiplied together, which makes problem 4 what? In big O terminology. N cubed. Mhm. And this might be something that you have to do if you've got like a triple nested loop. Like a nested loop with a nested loop with, sorry, loop with a loop inside of it with a loop inside that one. Which hopefully you don't have to write too much, but you might have to deal that if you're dealing with square matrices. Okay. So that's that. Now with regards to one of the other problems that you had to do that you're analyzing, which is the string to list of words. The question here that you have to ask yourself is, what is n? And I think it's easiest if you look at that like, is n, the n is the number of characters. Okay, so how many times are we checking each character? Right? Are we checking each character like once or twice, or are we checking each character against each other? And that's what you have to consider for that one. All right, so I've eaten up plenty of time, so let me stop that.